Okay, thank you, Anno. And thank you all for coming. It's sort of the middle of the afternoon. I'll try and not put you all asleep. So I'm not going to be talking about algorithms and stuff. I'm going to talk about the squidgy carbon units like us, how we program ourselves, how do we get better at doing things. So I want to start off with a question. Here's a really interesting quote. And if you read this, sort of take your time for a second and think, who said this and when did they say that? Was this last year? Was it sort of since 2000? Anyone willing to shout out which decade they think this was said in? 40s? 80s? 70s? Not yet? No one's got it yet? 60s. This was the 60s. Effectively, someone is describing TDD in 1960. And well, it wasn't 1960, it was actually a different year, 68. Who do you think said that? Walt Disney. Anyone know who won the first ever Turing Award? Does anyone know what the Turing Award is? Alan Perlis, 1968, this was said. Kind of interesting little bit back in history. We are kind of very interested in this industry because we don't seem to learn yet from our past. There's a few reasons for this. And I think there's some interesting cultural things going on with our industry. Like typically when we write code, I find a lot of code I come across looks a bit like this. We do kind of hack things a little bit. This was from Russia, but Russia's not unique. Here's the UK. There's supposed to be a fuse in there. Drill bit? We don't have a monopoly on this. How about Australia? There seems to be a pattern over the world in general. I think a lot of it comes down to this sort of thing. This seems to be the core of software engineering today. We copy and paste these things. Like, it's a bit funny in some ways, but here's something that's supposed to be serious. Mercedes-Benz, the new E-Class, they're bragging about how much code is in their car. If you can read some of the small print here, they're talking about there's much more code than there is in an F-22 Raptor fighter. There is way, way more code than there was in the space shuttle. This is not a proud thing. Like, they're even making advertisements about it. We're talking 100 million lines of code in a car. This terrifies me that there's that much code in a car, knowing how many bugs there is in code. So like, they're looking at 100 million. The new Tesla is looking at 300 million lines of code. We're just cranking this stuff out at a huge rate, but we don't tend to be doing that good of a job of it. I think there's some interesting questions around how we're evolving as an industry. So I'd like to kind of look at myself, look at teams I work with, work at how we can kind of get better, but things kind of stand out. And if you look at other disciplines, they're much more mature. They've been around a lot longer. So you think, like, how many generations have we been writing software? Sort of most people, they're not even a second generation programmer. I've only ever met 2 other third generation programmers in my career. And they actually tend to be very good because they've kind of been passed on, sort of going down the generations, and we're learning to get better. So what can we do to get better? Let's sort of address this. So we've had a number of attempts at this as an industry. Anybody ever been involved in one of these standards? I did a lot of this in the 1990s. We went from having crap to having well-documented crap. It's kind of the way we end up going. It's scary. I like to put it this way. We're kind of living in the era of software alchemy. It's a bit like physics in the 1600s. We haven't had the Newton come along yet to show us the way. We're still trying to work this out. We're kind of trying to turn lead into gold. Turn stuff in JavaScript, but yeah. So let's sort of take this forward. Let's look at it from an engineering perspective. I want to come back to, if I want to be an engineer, what is the core of this? If there's such a thing as software engineering, where does it come from? Or can we engineer ourselves? So if we're going to look at engineering, let's go back and actually do a bit of study rather than make this up as we go. Like, where does engineering come from as a term? Well, it's made up of two Latin words, and it's about devising clever things. That kind of is an interesting way of describing what we do. It was actually, the term of an engineer was first used around about the 1300s in France, and it's basically someone who operates some sort of military machine, a catapult, something like that, some instrument of war. And so most of engineering kind of comes from that. This is why we have the term civil engineering, because civil engineering is pretty much everything that wasn't warfare back in those sort of times, and we kind of move forward. But let's look into, what do engineers do? If we look up one of the definitions of an engineer, and what do they do? Well, engineers must work within constraints. That seems something we should be doing. I program a lot in Java. I feel very constrained. I wish I had more flexibility, but I don't. But if we look at these constraints, there's many different cases, and usually it's a case of limited resource, be that budget or time. We've got physical limitations, limitations of our own imagination to how we do things in other ways. Really important things are like, we need to be flexible for modification, flexible for the future. I think this is very true of what we do. Code is always code we're modifying going forward. We misuse terms. I'll come back to some of the misuse later on, but maintenance is a really good example of this. You don't maintain code. Code does not wear out. It doesn't require greasing or oiling. It doesn't degrade that way, but it does have other properties. But importantly, we got to be able to modify it. And even if you think you're working on a greenfield project, this week you're probably modifying code you'd written last week. So constantly being able to modify, understand, be able to read code becomes really important. And there's other factors in here. And particularly, I like this one on safety. So thinking about how do we make our code safer. And safety is a very wide sort of subject. And I'll finish up near the end by touching this because I think it's a very, very strong point. But then just wrapping it up again, it's about these constraints and how we work as engineers as we go forward. Some people will relate it to science. Let's take the words of someone who we probably all know, Albert Einstein. He summed it up quite nicely. Where scientists investigate the world, they're looking at what is already there. Engineers, we kind of create the future. And in many ways, that's what we do. We're building systems that are shaping our future and going forward. So where does software engineering fit into this? Well, anybody know where the term software engineering comes from? Any idea of when? Which decade? 70s? Just a little bit earlier than that. First piece of evidence I can find for it is in the 1960s. 67 to be precise. It was in this particular paper. Most people acknowledge this is where the term was actually coined. It was popularized by this great woman, Margaret Hamilton. She led a lot of the development on the Apollo space mission. Amazing inventions, things like priority scheduling, sort of a lot of what we do with testing all comes from her. And she instilled and made popular the whole idea of software engineering for a long time. She ended up being director of software at NASA, doing some great things. So in some ways, we kind of look at sort of like, where did some of our discipline come from? So Alan Perlis, the first guy I mentioned who got the first Turing Award, he's generally known as the grandfather of computer science, where in many ways, Margaret Hamilton is the mother of software engineering. And yet, we don't really understand our history in this subject, probably because we don't get kind of computer history courses at university. We just get dumped straight in with whatever's current, but we're not really learning and going forward. Go back again to 1968, and there was a really interesting conference. So NATO was trying to work out how to build better software, how do we learn from the past. And this conference was really interesting because they recorded the proceedings of it. And this paper is somewhere you can go and read. And I reread this again earlier this year. It's a wonderful piece and it's full of gold and really interesting things we can learn. Some of the most interesting people in the history of our subject were at that conference, and some of what they said was captured. So I want to go through and pick out a few things from this and see, like, what can we learn from the past here, and actually have we learned going forward? Take this for example. Someone was describing the design process is an iterative one. You flowchart until you understand the problem. You write code until you realize you don't. We go back, we redo the flowchart, and we basically just iterate. So Iterative development was understood in the 60s. Yet we went forward with waterfall. Even the waterfall paper said it was a bad idea, so we went forward with that. So failure, we didn't learn from that. Like design, talking about how reliability is a design issue. It's really, really key. We can't add in a lot of the quality attributes later. Like we even use bad words. I hate the term non-functional requirements. Because if you actually look at what non means in the dictionary, it basically points you to saying this is not the important stuff. We use the wrong words and the wrong words program behaviors. The quality attributes are key. Things like security, performance, usability, reliability, all of these things are so key and you can't add them on to design at the end. Like people would not go ahead today and build a bridge and not have an idea what's going to go across that bridge. We need to sort of think about these things. And I love the last bit, you might as well give up. If you don't build these things in, we need to be more professional. Other great quotes. Good systems that are presently working are generally written by small groups. More than 20 programmers working on a project is usually disastrous. 1960s, we knew this, and yet we keep throwing people at projects. Fred Brooks even wrote books about this, like Mythical Man Month, pointing out the problems that we have. Other good ones. So, begin with skeleton coding. Rather than aiming at finished code, the first 46 steps should be aimed at exploring. Like, we need to discover. It's all about learning. Some really interesting stuff in here. How do we approach these sorts of things? And then this sort of makes the point that we should check out the critical items, the really important stuff in our project. Lots of things that we just still don't do as normal practice. Here's another one of my favorites because I really have issues with this whole idea of having architects that don't code. They were talking about this in the 1960s. This really interesting quote where, like another interesting concept where they're trying to take from the Air Force. If you're a pilot, you have to fly so many hours per month to keep your wings. They're saying here that you should be writing a number of lines of code per month to be at a certain level. So this going out of our discipline and not writing code anymore, again, was being talked about even back in the 1960s. How do we get better at this? This is a bit of a dense one, but it's kind of interesting, where it's pointing out that the they and us, the them and us type concept, we hear this so often, the people in the business. People don't look into following what the business required and talk about them like some breed of cats living in some outer world. Most of the designers and manufacturers of software are designing, I think, for their own benefits. I've got a term for this. It's technical masturbation. So much of what we end up doing is we're not doing it for the customers, we're just doing it for our own pleasure, and sometimes very twisted pleasure at that. We've got to get better at this. We're not professional if we start doing these sorts of things. Estimation. Let's look at that. So we try to estimate. Here was a study of the first three Fortran compilers, the same team working on each of them, estimating and building them. What did we learn from it is over time, people do get better at estimation, but only if you're doing the same thing. If you're going to estimate something that you have not done before, the estimates are pretty much worthless. I've seen this a few times myself personally. I've built a number of transaction systems, a number of messaging systems, and you kind of get a bit better at estimating, but you still are not even close. So there's kind of a lot to be learned from that. So that's just some highlights I'm picking out from that paper. I recommend go back and read it. It's actually quite entertaining and slightly depressing at the same time, where things that you kind of think, yeah, we see this every day. It was seen 50 years ago. We just haven't quite learned and caught up yet. One of the other people who was at that conference was Dijkstra, and he's written some other really interesting pieces on this subject as well. Particularly, I like this one, where he talks on how do we teach computer science. And he talks about the cruelty in which it should be taught properly and some of the experiences he had about it. Like out of that paper, a couple of interesting points stood out. I like this one on radical novelty. where he explains that so much of how our education system works and what we have done for years, and I'm talking education system in the modern terms, I'm talking right through history, we teach by storytelling and we pass on things through metaphor and analogy a lot, and these are really, really good techniques, but they're not good for certain subjects. There's some subjects that there just is not metaphor and analogy that works for it, and he talked about this as the radical novelty. He believes that computer science is in this radical novelty category. Like, for an example of something else, he's talking about how if you try to use these analogies, you just end up with something that's woefully inadequate. Like, what is another example he was saying? These are quotes directly from his paper. He's talking about if you try to learn quantum mechanics or relativity, you'll realize that any existing physics doesn't help you. And it's the same sort of thing with computer science. Like, what other examples do we have out there besides things like quantum mechanics? Well, things like the atomic bomb or the pill, for example, contraception. When we come up with something that's so new, it changes everything that's from there before. It changes the whole fundamentals and ethics even, and things like it shakes politics, it shakes religion, it's all sorts of things. Like, what the internet has done to the world has so fundamentally changed how we all exist as a people, and a lot of this is down to the radical novelty. So that's it's a cautionary tale on how when we use metaphor and analogy, we have to be careful, like software maintenance being one of those examples. It actually programs us to think in the wrong way because we don't maintain the software that way. His other interesting points that I thought were great in this paper, one was the whole idea of divide and rule he talked about, which is basically decomposition. We have to get better at decomposition on an unprecedented scale. We've got to look at different ways of doing data decomposition, procedural decomposition, behavioral, all sorts of different ways. If we don't get better at that, it becomes really hard to divide things up. And if we can divide them up, then we can do things with larger teams. This is a lot of what's fundamentally the problem with saying we can't work in large teams. We can't deal with more than 20 people because we're not decomposing at a level. Like, that could be a huge, interesting talk on its own right. The other point that it really struck home for me was this amplification of changes point. Like, we can get one bit wrong in a program, and the program may have billions and billions of bits in it. One bit can cause a catastrophic failure where the whole thing doesn't work. There's nothing in human history like that. It's so unique in a way of going forward. So how do we deal with that? How do we test for it? How do we cope with it? How do we isolate the damage from those sorts of things? And these are things that we need to start thinking about to become proper engineering. And without this, how do we go forward? Well, if we kind of turn back to ourselves now, that's a kind of interesting sort of whistle-stop tour through some of the engineering history. How are people engineered? Well, we are fundamentally the product of our own experience. I'm a computer science major, that's what I studied at university. But I went to an interesting university that encouraged us to do other things. So we were encouraged to take other subjects, accountancy, a modern language, various other things. One of the ones I took was behavioral science. And I think it was actually probably one of the best choices I made at university. So I'm always kind of interested in dipping back to this. So if we look at, well, if we are the product of our own experiences, that is one way we can influence how we change ourselves. So change our experiences, give us different options. And something that I've discovered working on many, many projects globally, I've been writing software professionally now for over about 25 years, and I keep finding this uncomfortable truth on many projects. So often the success of a project is down to one or a small number of individuals working outside of the process. Often our processes are not helping us actually deliver. Now, that's not a good situation to be in. And why do we need to have these individuals who are kind of smart enough and see the opportunities but are willing to work against the system to get success? We need to be able to turn this around. We need to have that not the main way we get stuff done. But also, a lot of these individuals that I've seen that go against the grain have similar sorts of properties, similar sorts of things that they care about. And I'm going to cover this a little bit as we kind of go into the next section of this. So I want to look at three sort of basic areas of how we would engineer ourselves. So looking at what do we want to get experienced in, how do we approach that? where can we get those experiences, and then kind of how do we sort of assimilate this and deal with it. And that's kind of the bulk of what I want to follow into. So if we look at the what should we be learning? So if we're going to have these experiences, what's kind of interesting? Well, if you're going to write a lot of code, algorithms and data structures are so fundamental. I find that I go back to early programming I did even as a hobby back in the 1980s. I had to learn about algorithms and data structures. I still find almost every day as I'm writing code, these things are useful. At different times in my career, I've been asked, sort of going into a client, do you know WebLogic 7.3? I kind of think, no, I haven't used 7.3, but I used 6.5, and the client would be going, well, you haven't used 7.3. And it just seems like a bizarre conversation to be having. You can pick up the differences really quickly. So much of our technology goes out of date really quickly. Probably many people in this room have not even used WebLogic, and that's only sort of going back over a decade, which is not surprising. So what can we learn that's going to stick with us for the rest of our careers? Well, I think data structures and algorithms are some of those sorts of things. If it's just particular frameworks, they're probably going to be out of date really quickly. Even if you know like the latest version of C# or Java or Elm or whatever it happens to be, it'll probably stick with you for a while, but probably not for your whole career. If you're learning something like JavaScript or a particular library, it'll be out of date in a week. It's a bit like milk, it just perishes and goes. So where are we going to sort of learn some of this interesting stuff? Like going back to like the work of Knuth, it's still applicable today. It's advanced, we know more about these things, but a lot of that stuff is still applicable, still can be built on. Stronger than that, I think, is design fundamentals. A lot of people can kind of parrot, fashion, repeat what it means to have code that's decoupled, code that has got good cohesion, code that has separation of concerns, single responsibility principle. So some of the fundamentals that we need to care about in our design, but they don't practice it. They may be able to repeat those things. It's a bit like we learn to pass exams at school. That doesn't mean we know how to actually do that task and do it well. And I find like sort of reflecting back and looking at your code with a critical eye and saying like, oh, is that nicely decoupled? Like, how many different types of coupling are there? And think like, who off the top of their head knows how many types of coupling there are? Is there one? Is there many? More or less than 10? See, people aren't even screaming out. I'm not surprised because we just don't focus on these things, yet it does really, really matter. Like, who even has heard of connaissance? It's a type of coupling that's specific to object orientation. Like some real design fundamentals. It's worth going and looking up some of these sort of things. And like, don't feel bad you don't know. Most of the industry doesn't. We just don't focus on what's important. Yeah, we'll just copy something off Stack Overflow. That'll do. That's how we kind of do our jobs in some way. So it's worth going back and reflecting and seeing how we can do this. You get exposed to more of these kind of fundamentals if you look at different paradigms, because different paradigms tend to be based on some of these fundamentals. Like object orientation focuses on information hiding and encapsulation. Those are sort of things that are nice. Like things like immutability is useful. Functional programming will look at that and deals with it in a nice way. So just that we can learn from different concepts. In fact, even steal from different concepts. How do we even learn multiple things at the same time? Like a technique I found that's working out to be really useful is looking at problem space from many different dimensions, different perspectives. Like, for example, if you have to write your code in an object-oriented fashion because that's fitting in with the rest of the team, how about trying to write your tests in a functional style to use that as a different pattern? It gives you a different viewpoint on it. Things like formal specification are interesting in that they'll let you look at a problem in another way as well. It's not that you need to get it perfectly right, you get the different perspective. It's like working on your own versus going and talking to a colleague. It lights up different parts of your brain. You learn in lots of interesting different ways. So explore the paradigms, learn from them. Don't get stuck in a cul-de-sac in just one. Like the decomposition and abstraction is huge because we have to be able to deal with things at the right level of skill to be able to think about it. But we've got to look at practicing them. I keep finding that most people don't really look at decomposition in a good way because decomposition without a really good look at coupling It's kind of a bit strange if things are very, very highly coupled, you still can't break away from the level of understanding that you need. Same with abstraction. Abstraction has to make something more precise. It shouldn't be something that papers over the cracks and hides things, and we tend to use these things in the wrong sort of way. I think mathematics is fundamental to a lot of this, and I'm not talking about really complicated mathematics, just really simple stuff even. Like, as we move to having multi-core, the more and more we're doing of that, we have to write some code that runs in parallel. And if we start looking at tasks that are broken up and combined, it may be on a single thread where we're trying to get instruction level parallelism. Like, anybody wants to come and talk to me about this sort of stuff afterwards, huge passion of mine. It's like, even on a single thread, we have a lot of parallelism through our CPU because we have multiple execution units and multiple schedulers, and most people are just kind of blissfully aware. But the more your code has got less dependencies in the code itself, and what I mean by that is data dependencies on a single thread. So for example, if you've got 3 integers that need to be added up, those are commutative, they're also associative, and as a result, they can happen in parallel. So even though it may look like it's single-threaded and they have to happen in series, some of that stuff can happen in parallel. Subtraction is not commutative, so the compiler has got dependencies between the tasks. We can change some stuff at a really simple level to get much more out of our code. And then as we scale that up to task level parallelism, you look at something like streams and stream processing, we can do a lot if we have designs that are commutative and associative again. But if we end up with dependencies, we cannot scale the same way. There's some math that just hunts us down and stops us. And the future is we're going to have to learn this stuff, whether we like it or not. We kind of have got away with not learning it, mostly as an industry because of Moore's law and that clock speeds of processors have been increasing, but that's over. We're just going to keep going forward now with roughly the same CPU throughput, and we have to do things in parallel, and we have to do things more efficiently. We've got to save energy. We also have to learn business domains. That's a kind of interesting thing about our subject. It's very different from many others. We've got to do our own jobs and understand another domain and be able to understand it well so we can simulate that domain, which gives rise to a number of really interesting skill sets that we need. One of the most important being communication. We have to be able to work with other people. We've got to be able to do this sort of stuff well. And it's kind of interesting seeing Brian Little's talk the other evening where he was talking about the introverts and the extroverts and how we need to learn to communicate. This sort of stuff is really important. Unfortunately, a lot of the introverts who are going to be really good at coding have to go talk to customers. We have to work out how to get over that and do a better job at it, or form teams where we pass this information around in a good way and do this really well. I'm kind of starring in this one as well because as we move from our monoliths into a microservice world, we have to have lots of communication happening between our objects. And it's not just objects, all sorts of different components. If they're going to talk to each other, it's not just about learning RPC or messaging or something, it's the protocol of interaction. It's how these things have a conversation with each other. There's much more semantics to that than just how you get bits and bytes on and off the wire. We have to be able to deal with separation in time and space, and there's lots of really interesting points to this. Because we have these monoliths, we maybe don't like them, we think they're a big pile of steaming whatever at the moment. One thing's for certain, you take something that's big, it's got a certain surface area. It's only got so much surface area to let that smell out. You break this up into 1 million little microservices, you have a lot more surface area. Your world's going to stink a lot more. We just got to be aware of some of these things. Like, just don't blindly go into this. We can do wonderful things with distributed computing, but if we don't understand the protocols of interaction, like, who here has gone back and read any ITF papers on protocols? 4 or 5 hands? So little. There's gold in some of that stuff. Like, we have got bodies of knowledge in our industry where we know how to do some of this thing. We've got to learn from it. We've got to pass that knowledge on and do it well. If you just go from your monolith to your distributed system with all your little microservices and they start communicating and you don't understand the protocols of interaction, it's going to end up being messy. So that's stuff to learn. Where can we learn this? How do we go about learning? Well, kind of fundamentally, personal practice. The more we practice doing something, the better we get at it. But we got to practice doing the good things. If you keep doing the bad things over and over again, they become ingrained, they become reflexive. We've got to be questioning ourselves, questioning, are we doing the right things? Like, why is it a good idea to work just an 8-hour day and not work longer than that? Because as you get tighter, your practices start to fall off, they're not as good, and then you ingrain them as bad. We've got to start taking a lot more responsibility and practice in a good way. Even better, make it play, make it something we enjoy more, and we start dealing with it. Which kind of comes into the second point. It's where else can we learn? We can learn from people. And the teams and the people you work with are probably the biggest influence on doing stuff really well. There's lots of studies that show about kids doing well at school or not. It comes down to who their peer group is, who they're with. It's the same in our world. You either get lucky and you work with some good people, but one of the things we can do is take charge of some of that ourselves. If you think the company that you're working for is not giving you what you need, you can start talking to them about changing stuff, about getting better. But if they're not going to get better, you have a very simple choice to make, and that is you can choose to go somewhere else and get better. We have so much need for great software in our industry. Companies can't just keep doing a really bad job and surviving. The ones that do a better job will survive. Evolution has taught us that. It may not happen overnight, but it will eventually happen. We have to do things better. And so if you can't find somebody around you that's doing a good job within your own teams and stuff, find another team, go elsewhere. Research papers, also really interesting. We've got such great bodies of work out there. So you want to start learning stuff, you can't work directly with the teams for everything that you need to know. Where can you start finding some of this other cool stuff? Papers, there's lots of them. Like I've mentioned a few so far in this talk. We've got stuff going back to the 1960s. Don't be afraid to read papers on a given subject. People often ask, well, when should I go explore? What papers should I learn? Well, we all work on stuff every day. And sometimes you're working on a subject and you kind of feel, I don't really know enough to do this well. That little alarm goes off in your head. Your little taste alarm should be going off saying, I'm not that comfortable that I really know what I'm doing here. It's okay to listen to that and think, well, how do I find out? Rather than just paper over it or hack something out to make it happen, go do a bit of research then. There's a great world of stuff we can just Google for and go find. We also should be reading code. Code is a lot of what we do. We learn if we read other good code. Like Stephen King, the author, was once asked, how do I become a better author of books? And he says, read more. I think it's the same for us. Unfortunately, as an industry, we've done a lot of stuff with proprietary code that's in-house and closed source. This doesn't help us. The more we start doing things in the open, the more we can spread good examples of how to do things well. So that's also a great way to go learn. Go get involved in open source, or at least encourage your employers, if you want to change them, to start open sourcing stuff. I've been through a number of companies where we open source some of our products, and it made a huge difference to the quality of our code and how people were learning. I personally have learned massive amounts from working in open source, where people review your code, give you feedback, and you can get better as you do stuff, and just read other good examples that are out there. So let's read more and go and work out how to get better. Our projects are also interesting. So we have to work on projects. As we need to learn, one of the things that's important with it is give things time. Things need time and iteration to bake in. So when you're working on your projects, tackle the hard stuff first. Deal with the unknowns up front, because the sooner you start dealing with them, the more time you've got to work on them and get them right. Now, our instincts are often, let's wait to the end and do the difficult stuff at the very end of a project. It's kind of not a good way to go. It's a sort of Dilbert dinosaur approach. We end up running out of time, and this is why projects tend to run massively over time. If you start dealing with the hard stuff early, you'll know if you're not going to be able to do it on time much, much sooner, and you get more time to be able to refine that. I'll come back to that point. We've also got loads of online resources. And this is where I think things have fundamentally changed in our world. I remember going to job interviews, and I'd done a lot of interviewing for people in the early 90s to be employed. And one of the things we used to do a lot, besides this silly stuff of writing algorithms on whiteboards, we would ask people to recall facts. That used to be a useful skill, that you could remember stuff, because looking stuff up was a difficult thing to do. Like, go to the library was a physical exercise. Now we can Google for stuff. It's just right at our fingertips. So recall is a skill that's almost irrelevant these days. But we need to be able to realize, if we're going to pick something up, is it valuable? Is it the right thing to be doing? Are we going to go back to just copy and paste without realizing what we're doing? We have to be able to reason about what we have picked up from the internet and see, is it applicable to what we're doing? I'll touch on this now in a second. So, how can we learn? Which in the third part of this, the first thing that's probably the most important is we need time. If you're going to learn anything, you need time to do it. If you're working on projects and you're spending all of your time on repetitive tasks, you do not have the time to do the interesting things, the things that humans are good at. Humans are not good at the repetitive tasks. We kind of know this, but we need to get a lot more strict about it. Like, who here has got single push button deploy of their software? Good, the numbers are starting to go up. That should, I would like to think within 10 years that if that question was asked at any conference, that every hand would go up. It should be that way. We should have full CI, full continuous delivery of all of these things. Everything should be automated. We should not be doing regression tests by scripts. To quote Dave Farley, it's an abuse of human beings to do those sorts of things. Just automate everything, and then we don't make those silly mistakes over and over again, and we've got the time for the other stuff. Once you get the time, you got to focus on feedback cycles. So I work a lot in the high performance space. I have to look at the algorithms for a lot of how our software works, and queuing theory is fundamental to a lot of performance. It's exactly the same for teams and people, because that is just a system. We are all still fitting into a system. You optimize those in the same ways. Like, take time to go read up on queuing theory if you're interested, but the fundamental parts of it is to focus on service time and cycle time. It's actually, the service time cycle time is just two names for the same thing. It's the time from starting to do something to you get an answer from the thing being complete. And this is really important when we start to automate stuff or work in any sort of way. This is what Agile is fundamentally about. You have an idea, you be able to test it, you get feedback from it soon, and then you can react. And the shorter that cycle, the faster our ability to learn, and applies to pretty much everything that we do. Like, Agile is not about doing stand-ups every day, it's about shortening those feedback cycles. That's fundamentally what it's about, and we have to be able to do that across everything that we do. And we do that through experimentation. So we gotta be following the basic scientific method for approaching stuff. Is we have to have a hypothesis for how something works, then design an experiment to test that hypothesis and get the feedback that we need to have going. We need to be able to measure that feedback accurately, but also we need to be able to measure our live systems. We should be building telemetry into our live systems as a base thing without even thinking about it. Like, who builds telemetry into their systems as the first thing that they do? Few. Very, very few. We end up releasing software and it's a black box and we're trying to work out how it works. That's really hard to reason about. If you build telemetry and observability into your software, it becomes so much easier to reason about it, to see what it's doing, to debug it. You actually get faster in the delivery cycle. So these are the things that brings you back to time. We'll be able to do things much, much quicker. We get this evidence back. One of our flaws that we have to be comfortable admitting to ourselves is we tend to fit data to what we want the world to be, not how the world actually is. So we'll overfit stuff so easily. We've got to be honest about the data and apply scientific honesty. A great hero of mine and some of the work I love to read is Richard Feynman's work. There's some brilliant work he did on the Rogers Commission, which is the investigation into the Space Shuttle Challenger whenever it blew up. At the beginning of that, Rogers has documented all of the interactions of how they approach stuff, and in the early days he talked a bit about how Feynman is a pain. You see it all through his things. Feynman's a pain. He's constantly questioning. He doesn't take things that other people are just saying all the time. By the end of the report, completely different view. He says that Feynman had the greatest scientific honesty of anyone he ever met. And that's because he would very comfortably admit he was wrong in the face of new data. It's the data and the evidence is so important, but also look at it and don't overfit. So there's a lot to be learned from that. One of my favorite things to do whenever we start approaching any sort of interesting code is to get the process by which you interact with your code right. And this is, I find, a fascinating one. And I'll try and describe this fairly well. Where we get tasks to do. We take the task, we understand what it is, we write the code, we've written the tests at the same time, we're happy that it passed and we move on. We never go back and revisit and refine. And I think this is a fundamental flaw in how we approach any of our software development. And I've realized this a while ago that sometimes I was doing it and sometimes I wasn't doing it. And from now that I focus, that I make sure I work in a certain pattern, I've realized the quality of my own code has gone up immeasurably compared to before. Now, what do I do that's different now compared to what I used to do in the past? I'll now write the software for a task that I need to do, and I leave it and I go on and I'll write another task. And I'm not saying that's done. I'll do another task, I'll maybe do another task, and I'll come back and I'll reread and recheck my tests, and I'll revisit the whole thing again, and I'll spot stuff that I didn't see the first time round. And there's a really, really simple reason for this, and this is how our basic brains work. Whenever we go to do something, you can see this as simple. So take this as a really simple exercise. You go to write an email. It's an important email that has to go to a number of people. You write it. If you proofread it straight away and you hit send, what will happen is you will read what you think you've written, not what you've actually written, because your short-term memory is filling in what the things you have done. If you go to write it, you leave it for a day or so and then come back again and you reread it again. Your short-term memory has now been flushed. You're having to reread that again, and you're getting to read what you've actually written. And you'll see mistakes, you'll see things that you didn't realize before. The same thing happens with our code. This is such a simple little thing. I really recommend you try it. I seen the quote actually came about from Tony Hoare, who was one of the great computer scientists, another one of our Turing Award winners. He talked about writing papers the same way. He used to have a number of papers on the go at any given time, where he'd come back and he kept refining and revisiting them, and then he would publish them. So the time between starting the paper and it being released is longer duration. It's a similar amount of effort into it, but the quality was much higher and the throughput was even better. He was churning out papers really regularly of really high quality. But it's not a case of do a paper, publish it, done, do a paper, publish it, done. It's keeping the pipeline going with a revisit and a refine stage built into what you do. I find this is absolutely key to high performance, because if you start looking at your core modules and your core loops and things, you come back and you keep seeing ways you can make it more elegant. It's down to the great old statement of, if I had more time, I'd have written a shorter letter, and that's about the revisit and refine. So give it a go and see how you get on with it. And look at your code and sort of think, what can go wrong? Because if we want reliability built in from the start, we've got to think about how can things go wrong, and lots of stuff can go wrong. One of the papers I quite enjoyed reading a couple of years ago was this one, was talking about failures in the catastrophic failures in systems whenever they went into production. Lots of really interesting findings from this, particularly about configuration and mistakes people make with that. But the brilliant bit in it was around testing. That high 50%, I think it was around about 58% of errors that cause production outages could have been caught easily with a unit test. But people just hadn't tested them. What was much worse was 25% of the total outages were caused by errors that weren't even checked. We're talking about error handlers that had to-do statements in this, like, please, I need to fix this before production. It's really, really important, and never been addressed. That is not professional. That is not engineering. Yet this is very common of the problems that we end up doing in our industry. So what some of this comes down to, I think we've got an interesting war on complexity. We've got to work out how to make this much more efficient. One of the fundamental things is lines of code spent. Don't measure on productivity on lines of code. We've seen this enough as an industry, and I think one of the nicest ways to look at it is lines of code spent. There's a lot of evidence that shows that any individual can only deal with a project of about 10,000 lines of code at any given point in time. We can move on between modules, but that's the decomposition problem we've got to look at. We've got to keep our code small. Simple tip on this for measuring your teams, measure lines of code deleted. Even bonus people on lines of code deleted, and it's amazing what it does to the quality of your project. So kind of quickly in closing, don't feel bad. We are in the 1600s effectively of physics. This is the era of software alchemy. We're kind of working this out. But let's start working it out. Let's start doing better stuff. We can get a lot better at this, and it's kind of fun to do this. And on that, thank you very much.